Analytical Chemistry 1, Lesson 51. Edta titrations are very useful for measuring metal ion concentrations because they form such stable complexes because of the chelate effect. However, there are several important strategies that need to be explored in order to apply Edta as widely as possible. An important one is the use of auxiliary complexing agents. The first thing to understand is this table of fractional composition of the Edta in solution. There are 7 possible forms of Edta formed by the sequential addition of protons to the acid-base active sites. But it is only the fully deprotonated form that binds strongly with metal ions. By wanting to express the Edta in equilibrium expressions in terms of the total concentration of free Edta, we incorporate this alpha term to create the conditional formation constant. This decreases the magnitude of the formation constant. If it is an ion such as iron 3+, K starts off in the range of 10 to the 25. So even if we cut that down by, say, 10 to the 14, look at the value of alpha for pH equals 2, we still have a pretty large equilibrium constant of around 10 to the 11. But other ions will not fare so well. Zinc 2+, for instance, starts off around 10 to 16, and that same pH value of 2 would bring it down to around 1,000. This would not bode well for a titration under these conditions. But at pH of 12, the fractional composition is virtually all in the Y4- form. The conditional formation constant for zinc is still very large. Why do we not just do all Edta titrations at pH equals 12 and forget about this fractional composition problem? Well, it is the problem of unintended consequences. A solution at pH 12 has a very high concentration of hydroxide ions by definition, and hydroxide reacts with most metals to form precipitates. If we tried to titrate with Edta in high pH solutions, most metal ions would crash out of solution as solid precipitates before we could get any chance to put in any Edta. But even if we tempered the pH to a more modest hydroxide concentration to try to abate the hydroxide precipitation, there is still another reason to want to use a higher pH value. As we make a solution more acidic, lowering its pH, the conditional formation constant gets increasingly smaller, and the titration becomes increasingly like a weaker acid or base. When too weak, recall that titrating such an acid or base, the endpoint begins to blur as the concentration changes over an increasingly larger range of titrate addition. The same thing happens for complexation titrations. Here's the Edta titration of strontium in 5 different pH solutions. You can see the effect in the value of the conditional formation constant. A value of 10 to the 8 produces a sharp titration endpoint in a pH 10 solution, but it gets increasingly blurry as the pH drops. In the pH 6 solution, you can barely resolve it. A conditional formation constant of 10 to the 4 renders the titration to be of no value to us analytically. So there are very good reasons to want to titrate with Edta under basic conditions. But how can we deal with the troublesome hydroxide precipitation? The solution is to use an auxiliary complexing agent. There are other ligands that generally form stronger complexes with metals than does hydroxide, but at the same time the metal complexes they form are weaker than those formed with Edta. Ammonia, tartrate, citrate, triethanolamine are all commonly effective at this. They can be added to a metal solution and bind up much of the metal in their own complex, and at a sufficient concentration to inhibit formation of the hydroxide when the solution is buffered to a higher pH value. Upon addition of the Edta titrant, the Edta can outcompete the auxiliary agent and form the final Edta complex. As long as the auxiliary complexing agent keeps the metal away from the hydroxide but surrenders it to the Edta at the right time, the titration can be completed successfully at the higher pH value. But there is a cost. Just like the fractional composition of Edta accounts for the Y4- concentration, and we make provision for this by multiplying the formation constant by the fractional composition, the auxiliary complexing agent lowers the fraction of the metal ion that is in solution as the free metal with which the Edta can react. We need to know the fractional composition of the metal ion too. This is done by looking up the cumulative formation constants for the metal with the auxiliary agent, and use the similar expression as used for Edta. The end result is multiplied to the conditional formation constant to form the conditional formation constant, Kf double prime. This further decreases the magnitude of the formation constant, but it allows us to calculate with the total ETA concentration and the total metal ion concentration. Consider a cadmium EDTA titration. Kf is 10 to the 16.5, and at a pH of 9, the fractional composition of the EDTA is 0.0409. If we do this in an ammonia buffer, such that ammonia equals 0.1 molar, we hope we can carry out the titration successfully. Consider the initial cadmium concentration to be 0.01 molar. We add the ammonia and adjust the buffer to pH 9. Then we titrate the 25 milliliter aliquot with a 0.01 molar solution of EDTA. We've been able to look up a lot of the data, but we still need the fraction cadmium in the free state. We need the cumulative formation constants for ammonia with cadmium. Looking them up, we find that there are 4 sequential reactions. The fractional composition of the free metal ion uses the similar expressions for the acid-base fractional composition equations. The expression we use in the case of EDTA is for the fully dissociated form. For this one, however, we are interested in the unreacted form. Here's the expression we use, producing in this case, and given that we have an ammonia concentration of 0.1 molar, a fractional composition of 0.000781. Less than 0.1% of all cadmium is in the form of the free metal. The product of the formation constant, the EDTA fractional composition, and the metal fractional composition produces the conditional upon the pH, conditional upon the ammonia concentration, formation constant, which we label Kf double prime. With this modified value for the formation constant, we are able to perform equilibrium calculations using the total free EDTA concentration, that's all forms of EDTA except that in the complex ion, and using the total metal ion concentration, which is all forms of metal except that in the complex ion. So here's what we know so far. We determined the fraction of free metal ion, the metal ion not complexed by ammonia, in all its possible forms, and we've calculated the doubly conditional formation constant. But we need to compare this EDTA coordination complex formation process with the possibility that the cadmium will precipitate as the hydroxide. So we need the KSP value too. The doubly conditional formation constant is still quite large, so the reaction between the Y4- and the cadmium 2+ will still proceed quickly, even though both participants are at a low concentration. So what about the precipitation? The ion will precipitate if its reaction quotient is larger than the value of the KSP. The hydroxide concentration is set by the pH, which we chose to be 9. Therefore, pOH is 5 for a hydroxide concentration of 1 × 10⁻⁵ molar. The cadmium 2+ is the product of its formal concentration, we set it at 0.01 molar, and the fractional composition, which we calculated to be 0.000781. The cadmium available for reaction, that is the portion that's not tied up with ammonia, is 7.81 × 10⁻⁶ molar. We calculate the reaction quotient given these conditions, and we obtain the value of 7.81 × 10⁻⁻16, which is smaller than the KSP at 4.47 × 10⁻15. Therefore, the cadmium will not precipitate out. We now proceed with the EDTA titration. Using the doubly conditional formation constant, we have already accounted for the reaction with ammonia and the fractional composition of the EDTA itself, and we still have a formation constant of 10 to the 12. This is what chelation gets for you. We can do calculations using the total metal ion concentration and the total EDTA concentration. Here's the titration curve for these conditions. The transition is sharp and gives the correct equivalence point at 25 milliliters added titrant, since we set both concentrations to be the same at 0.01 molar. Do you see one reason for theoretically calculating a titration curve? If you had the task of determining the cadmium concentration in a sample, now and cadmium is a very toxic heavy metal, you could try different ammonia concentrations and pH values to find one that would likely give a good result. You could now try your actual titration with these conditions, pH of 9, ammonia at 0.1 molar, and you would anticipate successful results. This is a smart, knowledgeable scientist who has successfully completed a course in introductory analytical chemistry, and just like you. Now, one final word of warning. The real situation is still more complicated, and you should not be distressed if your actual titration did not work out as predicted. Why not? Well, there are possibly, or perhaps even likely, further reactions we have not considered. For instance, while we know we do not form the precipitate, it is still possible that some ion pairs formed with the cadmium, such as cadmium OH plus aqueous, that removes more cadmium from the free ion form, further reducing the effective formation constant. You might also have to consider the aqueous, but not precipitated form of cadmium dihydroxide aqueous. Without further information about the equilibrium constant values, you couldn't make a more accurate prediction. But you could still proceed with the idea that what you do know gives you a good starting point. Removing more cadmium may start to make the endpoint a little less sharp, but it is a good bet in this circumstance that it may still give good results. Chemistry is complicated, and from this course you have a good start on these foundational chemical principles, and expect to be able to build on them throughout your career.